All right, this video is all about work, specifically the math involved with work. So first, let's define work. So work is how we get energy into or out of a system. Right, so you could say like work is the change in energy of a system, whether we're adding energy or subtracting energy. So work for the universe is going to equal 0 because energy is conserved at the universe level. But we can define smaller systems than the universe. So for smaller systems, work can be positive, meaning we are increasing the energy. Work can be negative, meaning we are decreasing the energy, or the work being done can be 0, which means the change in energy is 0. Oops, change in energy is 0. Okay. So work is done when a force is applied over a given displacement. So if a force is applied to an object or system, and that force is responsible for displacing the object, then we can say that that force does work. Okay? So work is a scalar quantity, just like energy, but in order to do work, the force and the displacement must be partially parallel. That's not, I put an extra A in there. Partially parallel. Started to spell parallel. Okay? Meaning in the same direction, like X direction, Y direction. Okay? So the equation for work is W equals FD cosine theta. Okay? So work can be measured in joules or Newton times meters, since force times displacement is newtons times meters. Okay. Remember, F is the force, D is the displacement, not the distance. Okay. Remember, displacement is the straight line distance from our starting point, or how far we have traveled. And then this cosine theta takes into account the fact that the force and the displacement must be parallel. So this theta here is the angle between force and the displacement. Okay. So let's say I have a box being pulled across a surface by a force F. The box experiences a force of gravity, a normal force, and a force of friction. And I want to figure out the work done by those forces as the block displaces a distance x. Okay. So the first force I can find the work for is the force F. And I would do F d cosine theta. And in this case, since F and D are parallel to each other, my cosine is going to be of 0 degrees. So this is FD cosine of 0. And the cosine of 0 is 1. So the work being done is FD. Okay. Now, this will end up being a positive number. Okay. So that means that I have positive work done, which means my energy is increasing. Okay. Now that's the energy of the box-only system. Because I am applying a force over a displacement, okay, and that's causing an increase in energy. Okay. So now let's think about the work being done by the force of friction. So that's going to be force of friction, and that's applied over the same displacement. But here, the displacement's one way, and the force is the other way. So if we're opposite directions, then that means our angle is 180 degrees. So cosine of 180. And cosine of 180 is a negative 1, so this would be negative force friction D. So this ends up being a negative number. So that means I have negative work being done, and the force of friction results in an overall decrease of the box system. So next I have the work done by the normal force. And so I have FND, and then the normal force and the displacement are perpendicular, and we know that perpendicular equals 90 degrees. So this is cosine of 90, and the cosine of 90 is 0, so really the normal force does no work. So when a force is perpendicular to the object, it does no work on that object. So if we think about it, this normal force isn't responsible for changing the energy of our box system, right? Since we're dealing with the box system, we're really dealing with kinetic energy, and the normal force doesn't change the speed at all. So it makes sense that it does no work. Okay. Similarly, the work done by the force of gravity would be FGD cosine of 90 in this situation, which would again give us 0 work, so they would not change any energy. Okay. So those are the work done by the individual forces. We could also talk about the total work done, which we could find by adding up the works done by the individual forces. And I'm not going to include normal force and force of gravity because they do new work. Or what we could do is we could do the net force times the displacement times the cosine of theta. So the net force here would be that applied force minus friction times the displacement, and the net force would be, assuming this applied force is greater than friction, the net force would be in the same direction as the displacement, so I'd be at a cosine of 0, which would lead me to an overall positive work being done, an overall increase in total energy. So yes, the friction force alone would decrease the total energy of the system, but because this applied force does more work, the total energy of the system overall increases. Okay? Now, if there wasn't an applied force, or if the applied force was less than friction, then my energy would likely decrease. Okay? So that's total work. Another thing to point out is if we have a force applied at an angle, okay, and let's say that that force makes an angle theta with the horizontal, that would just be a straightforward FT cosine theta. That F and cosine, really what that's doing is that's combining for us to find the x component of that applied force, or the part of the force that is parallel to the displacement. Okay? So instead of finding the x component, it's kind of built into the equation already for us. Now this would result in a positive work, meaning an increase in energy, but that increase in energy would not be as large as if this force was just completely parallel. So let's talk systems for a second, because it's important to note that work is only done by forces external to the system. Okay, so let's say I have a block on a frictionless incline. We have a force of gravity and a normal force. Now, if my system is defined as the block only, okay, then that means that the forces that are external to that system are the normal force and the force of gravity. Okay, so those are my two forces that could do work. Okay. So since my system is the block only, any work being done, which in this case, work is going to be done by FG parallel, since my system is the block only, that's going to go into changing the kinetic energy. So I could say FG parallel D, and since FG parallel and D are in the same direction, I'm not going to include the cosine theta. I could set that equal to the change in kinetic energy. So let's say I have the same system. Boop, 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 boop. Okay. Again, on a frictionless surface. And let's say that my system is the block Earth system. Okay. Since the force of gravity is an interaction between the block and the Earth, that force of gravity is now internal to my system. So the only external force we have is the normal force. And the normal force is perpendicular to my displacement down the incline. So the total work being done here is 0. Now you might be wondering, wait a second, but I know the kinetic energy changes. It's the same thing as above. Well, here we would consider the change in gravitational potential energy, because that exists now in this system where it didn't before, equal to the change in kinetic energy. Okay. If I were to include friction, okay, then I could add friction to my external forces, and that change in UG plus any work done by friction would equal my change in kinetic energy. Okay. And this work done by friction would be negative. Okay. If I have a block on a spring, and let's say my system is the object and the spring, okay, my external forces here would be the normal force and the force of gravity, and if there's friction, friction. Right, Fg, Fm. Since the spring is in my system, the spring force is internal, right? Because it's the force between the spring and the block. So that means those are my only external forces. And those forces, or the only force of those three that's capable of doing work would be friction. So that would equal my change in energy, and depending upon where I was measuring, that could equal my change in spring potential or my change in kinetic energies. Okay. So if I want my work to change spring potential and kinetic, I need the object spring system. Okay. If I want the work done by the external force to change kinetic and potential and spring potential, then this would need to be the object spring Earth system. Okay. So external forces in this system would likely be things like friction or an applied force. Okay. So when we're thinking about our system and what does work, we have to remember that work is only done by forces external to the system. If the Earth is in our system, then that means gravity is internal now. If the spring is in our system, then that means the spring is internal now and doesn't do any work. If the spring and the Earth are in our system, we now consider their potential energies to be a part of our total energy. So it's not like that energy is like disappearing or those forces aren't acting. We're just kind of thinking about them as a different thing. Okay. The next video is going to go through some different ways to model work, and hopefully that kind of solidifies our understanding. But again, the big thing that we're keeping in mind is that work is FD cosine theta. Work changes the energy in our system, and work can only be done by external forces.